Welcome to our last week of doing some chemistry. This is module number 20, and we're going to look at acids and bases, their physical properties. So that just really means what are their characteristics. And we're also going to look at the pH scale. And that's a scale that we use. It's right down below here. We use that to tell us the level of what kind of acid or base it is, what's more acidic, what's more basic, etc. So I'm going to teach you those two parts in this module. So it covers section 7.2 and 7.3 in the textbook. And there's one extra thing you can do as you're working through this module. You can jump on the Explore Learning gizmo and you can see what the pH is for different substances. So it's just a virtual lab activity that you can work on. Okay, so to get us started, acids are covalent compounds. They generally have a hydrogen there. And when acids are in a solution, what makes them acidic is that they donate a proton or they donate a hydrogen ion into a solution. If you have a very strong acid, strong in terms of chemistry definition means that it's 100% dissociated. So all of the hydrogen ions and the chloride ions have completely broken apart from each other. That's what makes an acid strong, okay? Some common strong acids that maybe you know about are hydrochloric acid, hydrofluoric acid. Maybe you've heard of some of those before. And a common acid that we consider to be a weak acid is acetic acid or vinegar, okay? Now, the term strong and weak is very different than saying concentrated or dilute, okay? So those are terms that we keep separate in chemistry. Strong versus weak determines if something is dissociated 100% or not. Concentrated versus dilute refers to how many moles per liter you have. So you can have a strong acid that's very weak. Okay, very dilute, I mean. So that would be our great example here of hydrochloric acid. This is a strong acid, but my concentration is only 0.1 moles per liter. So that means that it's very dilute, but it certainly is strong because it dissociates 100%. Those hydrogen ions that get donated into a solution is what determines this term pH. You always see a little p and a capital H. That stands for the power of hydrogen. So the pH is something that you get a range of 0 to 14 on our pH scale. And anything that is right at a pH of 7 is exactly neutral. That means I have the same number of hydrogen ions and hydroxide ions. They balance each other out. They cancel each other out, if you will, and you end up with a pH of 7, okay? Anywhere you go on that scale towards the acidic side, you're going from 7 to 6 to 5 to 4 to 3 to 2 to 1 to 0. You're becoming more acidic as you go away from 7 towards 0, okay? That shows you that stomach acid and lemons are way more acidic than coffee or milk, all right? It's a logarithmic scale, so every jump on the pH scale isn't just a factor of 10, so it's not just 10 times 1 or 2 or 3. It's 10 times 10 times 10 times 10. So a good example of this, what we call a logarithmic scale, which you'll learn about in chemistry in grade 11 and grade 12, it really means exponential. So something that's a pH of 5 compared to a pH of 7 isn't just 10 times 2, so not 20 times stronger, more acidic. It's actually 10 times 10. So coffee is 1,000 times more acidic than distilled water because of this being a logarithmic, which is a mathematical property, okay? Anything that you move away from 7 towards 14, you are going in the basic range. You are becoming more basic or more what we say alkaline as you go from that neutral point of 7 towards the things that are more basic, okay? Bases. We recognize sodium hydroxide as a very characteristic base. It is strong, which means it dissociates 100%. And so in my container here of sodium hydroxide, all of the sodium and hydroxide ions have come apart. They've dissociated. It's an aqueous solution. And the concentration of the sodium hydroxide is the same as the concentration of the hydroxide ions. So we recognize acids by having a hydrogen ion They're proton donors. We recognize base as being something that accepts protons, but as far as grade 10 goes, we're just going to use it as something that has hydroxides. That's the definition we're going to go with for grade 10. Okay, once you've had a chance to do the reading and a few questions on the pH scale, this is the gizmo that I want you to try. Okay, I've added it to our classroom. It's just called pH analysis, and all you do is you change the substance that is in the container here. Okay, can you see that? That's coffee in there right now. I don't have to launch the app to be able to get it going, but you just change the substance and then you add the pH indicator paper to the substance and it'll tell you what pH it is. Okay, that indicator is exactly what this is. I'm going to show you what it looks like when I actually do it in real life, but that's your virtual lab activity that you can do for the pH scale. And again, that's just a brief overview of looking at the pH scale because really we just want to be able to do a little bit more chemistry and that's good enough for us this year. Okay, all right, now let's just go back to the lab activity that is on the second page of this handout, and you can just summarize this table as best you can. All you want to do are write down what are the characteristics of acids and go over 1, 2, 3, 4, 5, 6 different characteristics of what happens for all acids, and then you're going to summarize the same thing for bases. Okay, I'm going to go through each of these ones with you, the ones I can do at my home, and what I've got is I've got 4 little containers here and I've pre-filled them all with some acid. So I'm going to pull this up. This is not just water. Yes, it is a transparent, colorless solution. It is hydrochloric acid in here. It's not very strong though, right? It's a 0.1 molar solution. So we're good to go. I can use this at home, no problem. Okay. Here are some things that you can do to test if this unknown solution is acidic, and all acids will have the same characteristics. The first one, does it conduct electricity? Yeah. I have an apparatus in the lab that's a light bulb connected to 2 metal prongs at the bottom. If I stuck that apparatus into here, the light bulb would turn on. Yep, because it is a good conductor of electricity. The ions are mobile in here. It will conduct electricity, and you could test for that. Universal indicator. This is a container here that has a green liquid in it, and it changes color in the presence of an acid and the presence of a base. Okay, so I'm going to add a couple of drops to my acid, and you can see that in the presence of an acid, universal indicator will turn something red. Okay, that is a positive test for universal indicator and an acid. Now let's take my acid in I've just got another container right here. And I'm going to do the next one. This is phenolphthalein, okay? It is also a colorless solution. It is a very common indicator we use in the lab all the time. You will use this in grade 11 and grade 12 for sure. I want you to be able to remember that when you add phenolphthalein to acid, it's going to look like nothing changed. It is colorless. And that is how phenolphthalein acts with an acid. Wait till we get to the base. Next container, I'm going to use, here's where I've got indicator paper. Okay, I have 3 different kinds of indicator paper. I have red indicator paper. There's another indicator paper called blue indicator paper, and I didn't bring any of that home from school. Anytime you add an indicator paper to an acid, it will turn red or pink, okay? Same color. The blue one would also turn red. And then the last one is to use my pH paper. And here's what we would do if we were in the lab and we had lots of time. We would take our pH paper, we would dip it into our acid, and then we check the color with the color on the tube, and you can see that it's in the acidic range and it has a pH of 1. So this is pH paper, but again, we can use any version of the litmus paper that we need. Okay, so there is blue litmus paper, pink litmus paper, red litmus paper, and pH paper. They will all turn red in the presence of an acid. Are you seeing a trend? I hope so. Okay, the next ones are the lab activity ones where I don't have, I brought home some stuff, but my acid isn't strong enough. If you add magnesium and if you add sodium carbonate to a hydrochloric acid solution, you will get hydrogen gas and magnesium chloride. It is a vigorous reaction, it is fast, and that is characteristic for acids. The last thing for acids is that they have a bit of a squeaky feel to them. If you run vinegar through your fingers, you can feel that. If you've ever squeezed a lemon before, which I guarantee you have, put a little bit through your fingers, it has a squeaky feel. That's characteristic of all acids. If you weren't in the lab and you were at home and you wanted to test some acids, you'd recognize that they're sour, right? Lemons, tomatoes even, right? That's a very sour taste to them. And that concludes the characteristics of acids. Let's look at the ones that are the bases. Okay, first one. So let me move these out of the way for a second. And what I've got here, I've got base solution already put into my 4 beakers. So what base am I using? Sodium hydroxide. I'm not using the 1 molar solution because I didn't bring that home from the lab. All I brought home was a 0.1 molar solution, okay? Anything that you've got at home that you could test for bases, you sure can. You can actually use natural indicators to change color. If you've ever taken strawberries and add them to acid, or strawberries and add them to a soapy solution, they will change color. You can use flowers as a natural indicator, like anything that's got colored pigment. The best one is purple cabbage. You can boil purple cabbage down and get a purple cabbage juice. And if you add that to acids and bases, you get a beautiful range of rainbow colors there, because again, they indicate, or they let you know if you've got an acid or base present. Okay. First thing, if I took my base and I added my light bulb apparatus to it, you have ions in there. It is a good conductor of electricity. The light bulb would turn on. Next, let's add my universal indicator to my base. It went red in an acid and turns blue, purpley in a base. Okay? The more that I had in there, the stronger, the different range of color you would get. That is my universal indicator. Okay, really neat thing about the universal indicator is when I add the acid and the base together, okay, you can see what one I had more of. And I can go back and forth actually. If I add a little more base to this, watch. It'll eventually push it towards the other way, okay? That's the concept of neutralization, which we're gonna go over on Thursday. Okay, next one on the list is let's look at my phenolphthalein, okay? This is a beautiful color change, and again, we do this all the time. Add indicator called phenolphthalein, add it to a base, it turns fuchsia, bright pink, okay? You see that? That is what you do when you add phenolphthalein to a base, it turns fuchsia. What if I added more acid? If I went back and I added some acid to this, what would happen? I'm going to neutralize this. Watch. Colorless. It goes back and forth. That was just my indicator. I haven't done anything. There's nothing, no magic here. But watch, if I take this and what if I add more base? Let me take the base that has a bit of color in it anyway. Oh, I got to add more. Let me add some more base to this. And the more base I add, if I've got enough room in here, it'll eventually go colorless. And then the more base I add, all of a sudden I can get that fuchsia color back. Okay, so I can push that by neutralizing and adding more acid or base. The next one, so now we're still back on our bases. Let's use our paper. I'm going to do the pH paper. Okay, I'm going to get a clean one out. And when you add your pH paper to any of your bases, okay, here we go. It turns bluish. And again, how do you know if that's an acid or a base? You can tell, but your pH paper will go blue. The other indicator papers that I can use, remember, I could use a litmus paper. If I use blue or pink litmus paper, and you add it to a base, it turns blue. Do you see that trend, right? Acids red, base is blue, and that actually will happen, okay? So that's my indicator papers, all 3 kinds there. Magnesium and sodium carbonate, no reaction for those ones because acids won't react with them, okay? And then the last one would be if you took some base and rubbed it between your fingers, and you've probably seen this before if you've got some Vim, some cleaning solution, or a little bit of bleach on your fingers and then quickly run it under the tap, it feels slippery. Okay, and that's the characteristic difference between bases. If you weren't in the lab and you wanted to test it, put some baking soda on your tongue, you realize it's very bitter. Okay, so that's it for our acids and our bases module, and I'm going to do one more lesson on Thursday of neutralization. So you're working through the pH, gizmo, and then all of the characteristics of acids and bases.